This looks like one of those geometry problems where the circle seems to be hiding all the useful information from us. And at first glance, I might be tempted to start calculating the area immediately. But I cannot find the area until I know the radius. So my real goal is to uncover the radius first. Here is what I know. The shaded circle touches the left side, the top side, the bottom side, and the slanted side. The top horizontal segment has length 4, and the entire bottom horizontal segment has length 12. Both angles on the left are right angles, and the question asks for the area of the shaded circle. So let me call the radius of the circle r. Now, the touching points are extremely important here. Whenever a circle touches a straight line, that line is a tangent to the circle, and there's a very useful fact we can use. The radius drawn from the center to the point of tangency is perpendicular to the tangent. That means whenever I draw a radius to one of these touching points, I automatically create a right angle. Now look at the top and bottom of the figure. The circle touches both of these horizontal sides. Since the radius is perpendicular to each horizontal side, the distance from the top side to the center is r, and the distance from the center to the bottom side is also r. So the entire height of the figure is r plus r, which gives me 2r. This is our first important piece of information. Now I want to create a triangle that I can actually calculate with. The top side is 4 units long, while the entire bottom side is 12 units long. So the horizontal difference between those two lengths is 12 minus 4, which equals 8. That gives us a horizontal distance of 8 between the top right corner and the bottom right corner. Since the height of the figure is 2r, I can now think of the right-hand portion as a right triangle with one leg equal to 8 and the other leg equal to 2r. But I still need the hypotenuse of that triangle, and this is where the circle's tangent property becomes the key idea. Let me look at the slanted side carefully. The slanted side touches the circle, so it is another tangent. Now remember something very useful about circles. If two tangent segments are drawn from the same external point to a circle, those two tangent segments have equal lengths. I'm going to use that fact at both ends of the slanted side. First, consider the top right corner. The top horizontal side has a total length of 4. The circle has radius r, so the point where the circle touches the top side is r units away from the left side. That means the remaining piece of the top side from the circle's touching point to the top right corner has length 4 minus r. From that same top right corner, there is another tangent segment going along the slanted side until it touches the circle. Because tangent segments from the same external point are equal, that piece of the slanted side must also have length 4 minus r. Now, let's do exactly the same thing at the bottom right corner. The entire bottom side is 12 units long. The circle touches the bottom side r units from the left side, so the remaining distance from the touching point to the bottom right corner is 12 minus r. That is one tangent segment from the bottom right corner. Therefore, the corresponding tangent segment along the slanted side has the same length, which is 12 minus r. And now something really nice happens. The entire hypotenuse of our right triangle is made from these two tangent pieces. So its length is 4 minus r plus 12 minus r. Combining the constant terms gives 4 plus 12, which is 16, and combining the r terms gives negative r minus r, which is negative 2r. Therefore, The hypotenuse has length 16 minus 2r. Now, we have everything we need for our right triangle. One leg is 8, the other leg is 2r, and the hypotenuse is 16 minus 2r. This is the moment where the Pythagorean theorem becomes useful. Since we have a right triangle, the Pythagorean theorem tells us that the square of one leg plus the square of the other leg equals the square of the hypotenuse. So I can write 8 squared plus 2 r squared equals 16 minus 2 r whole squared. Now let's carefully simplify this. 8 squared is 64. 2r squared means 2r multiplied by 2r, which gives 4r squared. So the left side becomes 64 plus 4r squared. On the right, we have the quantity 16 minus 2r all squared. I have to be careful here because I cannot simply square 16 and square 2r separately and ignore the middle term. When we square a difference, we need all the terms. So I can multiply 16 minus 2r by 16 minus 2r. 16 multiplied by 16 gives 256. 16 multiplied by negative 2r gives negative 32r. Then negative 2r multiplied by 16 gives another negative 32r. Finally, negative 2r multiplied by negative 2r gives positive 4r squared. So the right side becomes 256 minus 32r minus 32r plus 4r squared. The two negative 32r terms combine to give negative 64r. So now our equation is 64 plus 4r squared equals 256 minus 64r plus 4r squared. And now we get the really satisfying part. We have 4r squared on both sides, so they cancel. This means the problem looked like it might turn into a quadratic equation, but it doesn't. After cancellation, I am left with 64 equals 256 minus 64r. Now I want r by itself. So I subtract 256 from both sides. On the left, 64 minus 256 gives negative 192. On the right, the 256 disappears, leaving negative 64r. So now I have negative 192 equals negative 64r. To isolate r, I divide both sides by negative 64. The negative signs cancel, and 192 divided by 64 is 3, so I get r equals 3. And that means we have finally found the radius of the circle. But remember, the original question is not asking me for the radius. It is asking for the area of the shaded circle. So now I use the area formula for a circle, which is area equals pi multiplied by r squared. We just found that r is 3, so I substitute 3 for r. That gives me area equals pi multiplied by 3 squared. 3 squared is 9, so the area is 9 pi square units. If I want a decimal approximation, 9 multiplied by pi is approximately 28.27 square units. So my final answer is 9 pi square units, or approximately 28.27 square units. Before we finish, I want to make sure the answer makes sense. A radius of 3 means the circle has a diameter of 6, and the total height of the figure is indeed 2r, or 6 units. The top segment is 4, the bottom segment is 12, and the difference between them is 8, which fits perfectly into our right triangle. The most important idea in this entire problem was not actually the Pythagorean theorem. The real breakthrough was recognizing the equal tangent lengths from the same external point. Once I noticed that, the two pieces of the slanted side became 4 minus r, and 12 minus r, giving us a hypotenuse of 16 minus 2r. Then the Pythagorean theorem did the rest, and the r squared terms canceled beautifully. So, whenever you see a circle touching several sides of a geometry figure, don't just stare at the circle and try to guess the radius. Look at the touching points. Use the fact that a radius is perpendicular to a tangent, and especially watch for two tangent segments coming from the same external point. That little property can turn a complicated-looking diagram into a simple equation. And once the radius is known, finding the area is just pi r squared, which brings us to our final result, 9 pi square units.